Okay, so this is video 3, unit 7, and we're going to just talk about some pendulums briefly. So a simple pendulum is another example that follows simple harmonic motion. So basically a simple pendulum is a string hanging from some wall or rack or something with a small mass at the bottom of it, and it would just swing back and forth, back and forth. And you can kind of see down here, I lost my pen, so bear with me, but if you see down here, you can see the forces. You see mg pointing straight down, and then you see the components of mg. You see mg cosine theta and mg sine theta, which would be right here or right there, same thing. And that is going to give us the force component of the weight. So it's tangent to the path of the motion. So the force is going to be negative mg sine theta in this case. So in general, the motion of a pendulum is not simple harmonic motion, but if we use small enough angles, then we can kind of model it as simple harmonic motion. So any angle less than 15, that's small enough, and what that does is it makes sine theta almost equal to theta, and so we can kind of assume that sine theta equals theta in those cases, and so the force then becomes negative mg theta, and then that obeys Hooke's law. Okay, so the main equation we're going to use for pendulums is this one. So it's the period, or t, equals 2 pi, and then the square root of L over g, where L is the length of the pendulum. And this is kind of weird because that means that the period of the pendulum only depends on length, which, if you remember, we showed at the very second day of class, we did that big pendulum swing, and we tried to see what it was dependent on, and it was only dependent on the length. And then obviously the force of, or the acceleration of gravity. So it depends on, it'll change depending on what planet you're on, but other than that, it's just the length of the pendulum. This is a little illustration that shows you how the simple pendulum is similar to a mass spring system. So when the pendulum is at its max, which it's the farthest from the equilibrium, which would be just hanging straight down, then that's the amplitude, and that would be like this spring being way out here. Equilibrium would be when the mass is hanging straight down, and then it would go back to the other side where it would be at the amplitude but compressed this time, and then you can see it would just keep going back and forth and back and forth. A physical pendulum, we're not going to talk too much about these, but a physical pendulum, just so you know, is you can make a pendulum out of anything you want, any object, and it will follow that the pendulum will rotate or oscillate along the center of mass. So that's what you're seeing right here. So wherever the center of mass is, that's the point where we can look at it being oscillating at that point. Alright, so we're going to do 2 examples. So the first one says, using a small pendulum of length 0.171 meters, a geophysicist counts 72 complete swings in a time of 60 seconds. What is the value of g in this location? So most of the time we're going to be using this equation. And my writing's a little bit bigger because I don't have the pen. And so if we already have the length, we're looking for g, so we just need the period. So if you remember, the period is equal to the number of, or the time, number of seconds, over the one swing, or over the number of swings. So to find the period, I'm just going to take the 60 seconds and put it over 72 swings, and I'll end up with 0.883. Whoa, let me try that again. So 0.833 would be our period. So then if we plug that in, we have 0.833 equals 2 pi L over g. And we know L is 0.171, so if we just plug that in, you end up with g equals 9.73 meters per second squared. So close to Earth's gravitational field, but not quite as large. Okay, and the second example, and this one's a little bit weird, so I just wanted to make sure you guys saw something like this before you do the homework. But it says a simple pendulum is 8 meters long, so there's our length. What is the period of the pendulum if it is located in an elevator accelerating downward at 6 meters per second squared? And this brings in kind of a new variable. It's called the apparent acceleration of gravity, or G apparent. I'll just put GAPP. But basically, I'll derive it in class, but it ends up being the acceleration of gravity minus the acceleration given. And so I'll show you how that comes out when we talk about it in class, but that's basically how you find the apparent g, and then this is the number you would use in your equation. So if we do that for this equation, we have the apparent g would be negative 9.8 minus negative 6. And I say negative because it's moving downward or accelerating downward. So that makes these two positive, which makes the apparent g negative 3.8. And if we plug that into that same equation we've been using, then we can find out what the period is. And when you plug it in, you end up with the period being 9.12 seconds. And again, we'll talk about this piece in class.